Welcome friends. In this video we will be looking at partial derivatives. So basically here we are looking at functions of two variables, say y equal to f of xy. In the previous video we have looked at some examples of functions of two variables. Now in case of function of one variable, that is what you studied in your plus 2 classes, y equal to f of x, for example y equal to x square or something like this. In such functions the derivative is defined like this: dy by dx is equal to limit delta x goes to 0 f of x plus delta x minus f of x by delta x. This limit, as delta x goes to 0, if it exists, we say that the derivative exists. You've already studied all the formulas, how to evaluate the derivatives of a lot of functions. Okay, now here we are going to move on to functions of two variables. So fx at xy is defined like this: it is equal to limit delta x goes to 0 f of x plus delta x, an increment in x, and y there is no increment, minus f of xy divided by delta x. So what is the rate of change of the function f when we are having small increments of x, of the variable x? That is what we are discussing here. Okay, now the geometrical significance we will be discussing in the coming slides. Okay, now how to evaluate a partial derivative like this: fx at xy is actually equal to d by dx of f of x comma y naught. That is, you have to evaluate the derivative of f keeping y as a constant, keeping y fixed. For example, suppose you are having some function, say z is equal to, say, x square into y. Now I have to, when I'm finding, that is, this is your f of xy. So when I'm finding fx, the partial derivative with respect to x, I have to treat y as a constant. So suppose I'm differentiating x square into 5. How will I differentiate it? D by dx of x square into 5. That will be equal to 5 x square. D by dx of x square is 2x into 5. The constant I'm keeping as such, it is equal to 10x. Similarly, fx will be equal to d by dx of x square is 2x, y I have to keep it as such. So this is the partial derivative. You have to consider y as a constant and then just differentiate terms involving x square. Okay, now similarly fy of xy, when I'm taking fy of xy, it is defined as a limit like this: f of x comma y plus delta x minus f of xy by delta y. F of x comma y plus delta y minus f of xy by delta y. So what is the rate of change of f when we are having small increments of y? Okay, now we will move on to some examples how to evaluate such derivatives, and then we will move on to other topics. Okay, so first let us consider this function f of xy is equal to 2x cube y square plus 2y plus 4x. Now first I will evaluate fx, the partial derivative with respect to x. Now as I told you, I have to consider all y terms as constants. Okay, so this y is a constant here, this y is a constant here. Okay, so these you have to treat it like any other number, like 5, 6, something like that. Okay, now when I partially differentiate this, 2 into what is, so it is equivalent to writing like this: d by dx of this whole function treating y as a constant. So these are constant terms, so I'll write 2. What is derivative x cube? It is 3 into x square, and the constant term I'm writing it as such, plus what is derivative of 2y with respect to x? So as I told you, y is a constant, so 2y, the derivative will be 0, plus 0 plus what is d by dx of 4x? It is 4. Okay, y I am treating it as a constant, so 2 into y is a constant. Derivative of 2y becomes 0. Now here derivative of 4x with respect to x is 4. So the answer is 6x square y square plus 4. Now the same function, if I am trying to differentiate it with respect to, say, y, fy of xy, suppose if I am trying to find fy of xy, then we have to consider x cube, all x terms as constants. So x cube and x are constants. So 2x cube is a constant coefficient that I am writing it as such. Derivative of y square is 2y plus 2 into derivative of y with respect to y, that is plus 2, plus now x is a constant, so 4x is also a constant, so derivative of 4x with respect to y is 0. So this is equal to 4 into x cube y plus 2. Now if I have to find the partial derivative fx at 1, 3, all I have to do is just substitute x equal to 1 and y equal to 3. So 6 into 1 square into 3 square plus 4. So 9 into 6, 3 square, yes, 6 into 1 square plus into 3 square plus 4. So 9 into 6 plus 4. So 54 plus 4 is 58. Now here similarly, if I have to find fy at 1, 3, what I have to do is I have to replace x is equal to 1 and y equal to 3. So 4 into 1 cube plus into 3 plus 2, that will be equal to 4 3 is 12 plus 2, which is equal to 40. So these concepts are discussed in this question here. Find fx of xy and fy of xy for this function and use those partial derivatives to compute fx of 1, 3 and fy of 1, 3. Now keeping y fixed and differentiating with respect to x yields something like this. So what we are doing is we are differentiating with respect to x, considering y as a constant. Okay, so here 2y square is a constant, derivative of x cube is 3x square. Here 2y is a constant, so differentiating with respect to x, it becomes 0. Here 4x, the derivative is 4, derivative with respect to x. So we are getting 6x square y square plus 4. Similarly, we did the second question also, and we found out fx at 1, 3 and fy at 1, 3. Now we will move on to some notations. So suppose if we are having z equal to f of xy, suppose if we are having z equal to f of xy, then the partial derivative, the notation of partial derivatives is something like this: dou by dou x. This represents partial derivative with respect to x, and dou by dou y. This represents partial derivative with respect to y. So instead of d by dx and d by dy, we will be having dou by dou x and dou by dou y. Okay, so when I'm taking partial derivatives, you can either write, so first for this function z equal to f of xy, if I want to write the partial derivative with respect to x, I can write either the partial derivative as dou z by dou x or as dou f by dou x, because z equal to f of xy. So the function names are either z or f. Okay, similarly when I'm writing partial derivatives with respect to y, I can either write dou f by dou y or dou z by dou y. These are partial derivatives with respect to y. Now if I want to evaluate these partial derivatives at a given point, I can use any of these notations. For example, I can write, say, dou f by dou x at the point x equal to x naught, y equal to y naught, or I can write dou f by dou x at x naught, y naught, something like this, or I can write, say, dou f by dou x at the point x naught, y naught. Similarly, I can use all these notations with z also. So I can use any of these notations to denote the partial derivatives at a given point x naught, y naught. Okay, now we will use some product rule, all those things in evaluating partial derivatives. Okay, so here we have this function here, z is equal to x raised to 4 into sine xy cube, x raised to 4 into sine xy cube, we will find the partial derivatives dou z by dou x and dou z by dou y. Okay. Okay. So what is dou z by dou x? Dou z by dou x, I'm partially differentiating with respect to x, so I'll have to use the product rule. So it is x raised to 4 into dou by dou x of sine xy cube plus sine xy cube into dou by dou x of x raised to 4. Okay, so this is equal to dou by x raised to 4 into, we know this is a composite function, so dou by dou x of sine is cos, so we have cos of xy cube into dou by dou x of xy cube. Now what is dou by dou x of xy cube? Y, I have to treat it as a constant. Okay, so dou by dou x of xy cube is just y cube. X is the variable, y is a constant, so dou by dou x of x is 1, so 1 into y cube plus sine into xy cube, dou by dou x of x raised to 4 is 4x cube. So this answer comes out like this: x raised to 4 into y cube cos xy cube plus 4x cube into sine xy cube. Okay, so this is the first part of the problem. We found dou z by dou x. That is what is done here. Dou by dou x of x raised to 4 into sine xy cube. So first function into the partial derivative of the second plus second function into partial derivative of the first. Okay, so we have it like this: x raised to 4 into cos xy cube into y cube plus sine xy cube into 4x cube. So we are getting the same answer: x raised to 4y cube into cos xy cube plus 4x cube into sine xy cube. Now we will find the partial derivative with respect to y. Okay, so we have dou z by dou y is equal to x raised to 4 into dou by dou y of sine xy cube. Now we have to consider x as a constant and y as the variable, plus sine xy cube into dou by dou y of x raised to 4. Okay, so I could have very well skipped the step because x raised to 4 is a constant, so it comes out to be 0. Okay, so x raised to 4 into dou by dou y, again I have to, it is a composite function, so cos xy cube into dou by dou y of xy cube, so that is x into 3y square, x is a constant, into 3y square plus I have sine xy cube and dou y of x raised to 4, x is a constant, so into 0. So this is equal to x raised to 5, 3x raised to 5 y square into cos of xy cube. Okay, so that is what is solved above. Okay, you see the same thing, dou by dou y of x raised to 4 into sine xy cube, x raised to 4 into dou by dou y of sine xy cube plus the first function into derivative of second. Derivative of the second, this term x raised to 4 is a constant when I'm partially differentiating with respect to y, so it becomes 0, hence we are arriving at the answer 3x raised to 5 y square into cos xy cube. Okay, now we will look at the geometrical interpretation of the partial derivative. Okay, fx at x0 y0 is actually the slope of the surface in the x direction at x0 y0, and fy of x0 y0 is the slope of the surface in the y direction at x0 y0. Okay, so if you look at this figure here, this given surface that you see here is our surface f of xy. Okay, this surface here. Now when I'm asking you to find fx at x0 y0, what is actually happening is, you just suppose I'm cutting this surface here with a plane that is y equal to y0. Okay, suppose I'm cutting this surface with a plane, it will make a cross section like this. It is a curve which we are calling as c1. This is that given curve. Okay, now this is the point x0 y0, so fx at x0 y0 is actually slope of this curve at the point x0 y0. Okay, so I'll repeat again, this given surface, this is the surface f of xy. Okay, when I ask you to find fx at x0 y0, what is actually happening is I am actually suppose we are considering a surface or a plane which is y equal to y0. Y equal to y0 will be a plane like this. I am cutting the surface by that plane, and it is making the cross section, which, and that curve is, I am going to call it as c1. The cross section is going to be a curve c1. So fx at x0 y0 is the slope of that curve at the point x0 y0. Similarly, when I am finding fy at x0 y0, so what is happening is, suppose we have a surface like this, which we are calling it as f of xy, and suppose we are cutting that surface with a plane which is x equal to x0, then it is making a cross section which is a curve, say c2. This is that curve. So the slope of that curve at the point x0 y0 is fy of x0 y0. Okay, so what is fx at x0 y0? Fx at x0 y0 is the slope of the surface in the x direction. When I move in the x direction, what is the slope of that surface? And fy of x0 y0 is the slope of the surface in the y direction. So what happens? What is the slope of the surface when we are moving in the y direction? So if you are asked questions like this, find the slope of the surface z equal to f of xy in the x direction at the point 1, 2, what do you have to do? You have to find fx at 1, minus 2. Okay, so here in the first question, you are asked to find the slope of the surface z equal to f of xy in the x direction at the point 1, minus 2. So what you have to actually find is fx at 1, minus 2. This is the slope of the surface in the x direction at 1, minus 2. Now at the point 1, minus 2, they are asking you to find the slope of the surface in the y direction. So you have to find fy at 1, minus 2. That is the slope of the surface z in the y direction at the point 1, minus 2. So it is given to us, f of xy is equal to x square y plus 5y cube. Okay, so we will first find fx. What is fx of xy? Fx of xy is equal to, we have to consider y terms as constants, and then x is our variable. So derivative d by dx of x square is 2x into y plus d by dx of 5y cube, or dou by dou x of 5y cube. So what is dou by dou x of 5y cube? Y is a constant when we are partially differentiating with respect to x, so plus 0. So it comes out to be 2xy. Now what is fy of xy? Fy of xy is dou by dou y of xy, which is equal to, we have to consider x terms as constants, so these will become our constants, and y is the variable. So x square into dou by dou y of y is 1. X square into 1 plus dou by dou y of 5y cube. So 5 into dou by dou y of y cube is 3y square. So here we will be getting x square plus 15y square. Now find the answer to the first question, that is fx at 1, minus 2. So what you have to do? You just substitute x equal to 1, y equal to minus 2. So 2 into 1 into minus 2, which is equal to minus 4. Now second is fy at 1, minus 2. So you substitute x equal to 1, y equal to minus 2. So 1 square plus 15 into minus 2 square. So 15 into 4. So 60 plus 1 is 61. So the slope in the x direction is minus 4. The slope in the y direction is 61. So what does that mean? That means in the x direction, the function is decreasing at the rate of 4 units per increase in x, and in the y direction it is increasing at the rate of 61 units per unit increase in y. So when x is increasing by 1 unit, f is decreasing by 4 units in the x direction. Okay, so similarly when y is increasing by 1 unit, f is increasing by 61 units in the y direction. Okay, now we will look at implicit differentiation. Okay, so when we are given with functions like this, say for example x square plus y square plus z square equal to 1, there are two ways in which you can differentiate this function partially. That is, there are two ways in which you can partially differentiate this function. One is you can write this as z equal to square root over 1 minus x square minus y square, and then you can find dou z by dou x, and you can find dou z by dou y. Okay, so instead of this is called explicit function, this is called the explicit representation of the function, and we are differentiating it as such. But other than that, if you are given with a function like this, say for example x square plus y square plus z square equal to 1, we can differentiate this directly. So suppose I'm finding dou by dou x of this whole equation. So what will happen? What is dou by dou x of x square? It is 2x. What is dou by dou x of y square? When I'm partially differentiating with respect to x, y is a constant, so this becomes 0. Plus the last part, when I'm partially differentiating z terms with respect to x, you must keep in mind z is a function of x and y, so it will become 2z into dou z by dou x. This is equal to dou by dou x of 1 is 0. Okay, so this last part you should keep in mind, z is a function of x and y. Okay, so when I'm differentiating z partially with respect to x, z is the dependent variable, so we should write 2z into dou z by dou x. Actually that term is there with every term, 2x into dou x by dou x, but dou x by dou x is 1. Here it is constant, so we are writing it as 0. Here we have to write 2z into dou z by dou x equal to 0. This part you should keep in mind. So dou z by dou x will be equal to minus 2x by minus 2z, which is equal to minus x by z. Okay, you have done this already. So for example, in functions of one variable, suppose you are having say x square plus y square equal to 1. What will you do? Y is a function of x, so 2x plus 2y into dy by dx equal to 0. That will be its derivative. Similar terminology you will have to use here also. Now similarly, we will partially differentiate that with respect to y. So dou by dou y of x square plus y square plus z square equal to 1. If I am partially differentiating this whole equation, it will be dou by dou y of x square is 0 plus dou by dou y of y square is 2y plus dou by dou y of z square is 2z dou z by dou x, 2z dou z by dou y equal to dou by dou y of 1 is 0. Actually we should write it like this. This is equal to, the right hand side I should write dou by dou y of 1. Okay, instead I'm just emphasizing the fact that we are actually partially differentiating the whole equation. Okay, so here we have dou z by dou y is equal to minus y by x. Now let's look at this question. Here they have given you the question, find the slope of the sphere x square plus y square plus z square equal to 1 in the y direction at the points 2 by 3, 1 by 3, 2 by 3. So they have given you the points x, y, z, and 2 by 3, 1 by 3, minus 2 by 3. So instead of writing it explicitly and then differentiating it, we have directly differentiated it. Okay, so we have that is called implicit differentiation. Now we will find the value at these points. So x is 2 by 3, y is 1 by 3, z is 2 by 3. That is the first point. So 2 by 3 minus 2 by 3 by 2 by 3. So that is what we have to do first. X, y, z. So minus x by z, you evaluate first and then you get the answer. So these answers are given here. Substituting the y and z coordinates of the point 2 by 3, 1 by 3, 2 by 3, and 2 by 3, 1 by 3, minus 2 by 3 in the expression, we find that the slope at the point 2 by 3, 1 by 3, 2 by 3 is minus 1 by 2, and the slope at 2 by 3, 1 by 3, minus 2 by 3 is 1 by 2. Okay, we are substituting at these points. At slope in the y direction is asked first. Okay, so they have not asked you to find dou z by dou y, so this part you don't have to evaluate. This part you don't have to evaluate. You just have to evaluate this dou z by dou y. They've asked you to evaluate in the y direction. So dou z by dou y at the first point. What was the point? 2 by 3, 1 by 3, 2 by 3. At this point, dou z by dou y will be equal to say minus 1 by 3 by 2 by 3. Y coordinate by z coordinate. This is z. Okay, I think I made a mistake there. So this is z. We are having 2z. So that is minus 1 by 2. Now those are at the other point. What is the second point? 2 by 3, 1 by 3 and minus 2 by 3. So at that point, dou z by dou y is equal to minus y by z, that is minus 1 by 3 by minus 2 by 3, which is equal to 1 by 2. So slope in the y direction at the point 2 by 3, 1 by 3, 2 by 3 is minus 1 by 2, and the slope in the y direction at the point 2 by 3, 1 by 3 minus 2 by 3 is 1 by 2. Okay, now we will look at notations in case of the in case of functions of these three variables. Okay, so suppose we are having w equal to f of x y z. This is the notation, w equal to f of x y z. So don't get confused with these notations. Okay, so for example, in one variable case you are having y equal to f of x. So x is the independent variable, y is the dependent variable. When it comes to two independent variables, this y actually becomes a dependent variable. So z equal to f of x y. So here x and y are independent variables, z is a dependent variable. Again, when we are coming to three variables, you have w equal to f of x y z. So here x y z, all of them are independent variables and w is the dependent variable. So don't get confused. When you see x y z and w, you must understand directly that x y z are the independent variables and w is the dependent variable. When you see x y and z, you must understand that x and y are independent variables, z is the dependent variable. That is how you must understand. So in this case, the partial derivatives are actually written like this: fx, fy, fz. There will be three partial derivatives, or in terms of w, you can write it as dou w by dou x, dou w by dou y, and dou w by dou z. That is in this dou notations. Now we will find out some partial derivatives in cases of functions of three variables. So we have this function here, f of x y z is equal to x cube y square z raised to 4 plus 2xy plus z. Now here, when I'm finding fx, that is partially when I'm differentiating with respect to x, you must understand y and z I'm going to treat it as constants. So when I'm partially differentiating a function with respect to x, y and z here are constants. Okay, so both of them are constants here, y and z. So y here is a constant, z here is a constant. So that will be equal to dou by dou x of x cube is 3x square, and y square z raised to 4, it is a constant, I'm writing it as such, plus 2xy. So 2x, dou by dou x of 2x is 2 and y is a constant, plus dou by dou x of z, z is a constant, so dou by dou x of a constant is 0. So you're getting the answer as 3x square y square z raised to 4 plus 2y. Now similarly, when I'm finding fy of x y z, you must understand y is the variable, x and z are constants. Okay, so here x cube z raised to 4, both of them are constants. So x cube into dou by dou y of y square is 2y into z raised to 4, plus here again y is the variable, x is a constant. So 2x into dou by dou y of y is 1, plus z again is a constant. So dou by dou y of y is 0. So the answer comes out to be 2x cube y z raised to 4 plus 2x. Now when I'm finding fz of x y z, you must understand x and y are constants, z is a variable. Okay, so x cube y square is a constant, z raised to 4, dou by dou z of z raised to 4 is 4z cube, and plus dou by dou z of 2xy, x and y are constants, so that term becomes 0, plus dou by dou z of z is 1. So the answer comes out to be 4x cube y square z cube plus 1. Okay, now if you are asked to find, say, at some specific point, say fz at minus 1, 1, 2. You just have to substitute x equal to minus 1, y equal to 1, z equal to 2. So the answer comes out to be 4 into minus 1 cube into 1 into 2 cube plus 1. Okay, so you will have 8 into 4, so 32. So minus 32 plus 1, which is equal to minus 31. Okay, so this is the example 10 which is discussed in the textbook. Okay, example 10. Now we will move on to one more question here using functions of 3 variables, and the question is this one: f of rho theta phi, f of rho theta phi is equal to rho square into cos phi into sine theta. Okay, so first I am finding f rho of rho theta phi, that is rho is the variable, theta and phi are constants. So dou by dou rho of rho square is 2 rho into I have cos phi and sine theta, both of them are constants. So the answer is 2 rho into cos phi into sine theta. Now when I am finding f theta of rho theta phi, you must understand theta is the variable, rho and phi are constants. So we have rho square into, now what is dou by dou theta of cos theta, sorry, here the term is sine theta. What is dou by dou theta of sine theta? It is cos theta. Rho square cos phi is a constant, rho and phi are constants when we are partially differentiating with respect to theta, and dou by dou theta of sine theta is cos theta. Now similarly, when we find f phi of rho theta phi, you must understand rho and theta are constants. So rho square into, what is dou by dou theta of cos theta, cos phi? It is minus sine phi. Minus sine phi into cos, sorry, into sine theta. Our original function is this one. Okay, rho square into dou by dou phi of cos phi is minus sine phi into sine theta. So this can actually be written as minus rho square sine phi into sine theta. Now we will move on to higher order partial derivatives. That is, we up to this point we were doing only first order partial derivative. Now we will move on to second order partial derivatives. For example, suppose if I am having a function like this, z equal to f of xy, first order partial derivatives are just, say, I can write fx or I can write dou f by dou x. Similarly, the partial derivative with respect to y is fy, or I can write dou f by dou y. Now the second order partial derivatives, suppose again I am differentiating this with respect to x, so it will be fxx, or equivalently dou square f by dou x square. Okay, and suppose again this equation number 1, suppose I am differentiating it with respect to y. So fx I am differentiating it with respect to y, so the notation is fxy, or equivalently in other terms I am differentiating dou by, so if in the other notation, so dou f by dou x I am differentiating again with respect to y, so that becomes dou square f by dou y dou x. So do you see the difference in notation here? With this notation the term is fxy, and with the other notation, dou notation, the term is dou square f by dou y dou x. See the ordering of terms. Here x comes first, y comes second. Here dou y comes first, dou x comes second. Okay, because it is dou by dou y of dou f by dou x. Here it is fx, and that fx I am differentiating partially with respect to y. Similarly, we will look at the partial derivatives of fy. Okay, so fy, the term was fy is dou f by dou y. Now second order partial derivatives. Again, suppose this equation, if I am differentiating with respect to y, so it is fyy. So it is just dou square f by dou y square, because it is dou by dou y of dou f by dou y. Now if I'm partially differentiating that with respect to x, so it is fy, and that I'm partially differentiating with respect to x, so the notation is fyx. In the other notation it is dou f by dou y, and that I'm partially differentiating with respect to x, so the notation is dou square f by dou x dou y. Okay, here again you can see the difference in notation. Fyx is the notation in this form, and dou square f by dou x dou y is the notation in this form. Here y comes first, x comes second. Here dou x comes first, dou y comes second. Okay, now we will do some problems using the second order partial derivatives. So here the function is f of xy is equal to x square into y cube plus x raised to 4y. Okay, so first we will find dou f by dou x and dou f by dou y. So what is dou f by dou x? Dou f by dou x, I have to partially differentiate this equation with respect to x. So I'll be getting dou by dou x of x square is 2x into y cube, plus dou by dou x of x raised to 4y. I'll have 4x cube into y. So this I'm going to call as my first equation. Now again that given equation, suppose if I'm partially differentiating with respect to y, then what will happen? It is dou f by dou y. So dou by dou y of x square y cube. X square is a constant. Y cube, the derivative is 3y square. So 3y square plus x raised to 4 into dou by dou y of y is 1. Now we will find all the mixed partials. Okay, partial derivatives. We will find all the mixed partial derivatives now. Now, what is dou square f by dou x square? Dou square f by dou x square, we know it is dou by dou x of dou f by dou x. Okay, that is dou by dou x of this part, 2xy cube plus 4x cube y. So what is the answer? It is dou by dou x of 2x is 2, so we will be having 2y cube plus dou by dou x of x cube is 3x square, so 4 3 is 12x square y. Similarly, suppose if I am finding dou square f by dou y dou x, so that is actually dou by dou y of dou f by dou x. Okay, so that is dou by dou y of 2xy cube plus 4x cube y. Now you have to differentiate that partially with respect to y. So that is 2x into dou by dou y of y cube is 3y square. So 6xy square plus 4x cube into dou by dou y of y is 1. So I'll just be having 4x cube. Now similarly, let's differentiate the second equation with respect to x and y. Okay, so suppose if I have to find dou square f by dou x dou y, what will be the term? That will be equal to dou by dou x of dou f by dou y, which is equal to dou by dou x of 3x square y square plus x raised to 4, which is dou by dou x. So 3 to 6x y square plus 4x cube. Okay, 6xy square plus 4xy cube, because I'm partially differentiating with respect to x. Now similarly, suppose if I'm partially differentiating with respect to y, the second equation, what will happen? I'll be getting dou square f by dou y square. That is, I'm partially differentiating that again with respect to y. Dou f by dou y, again I'm partially differentiating with respect to y. So I'll be having dou by dou y of 3x square y square plus x raised to 4, which is equal to, I'll be having 6x square y. That's all. Okay, so these are the terms which are given here. Okay, we have dou square f by dou x square, dou square f by dou y square, dou square f by dou x dou y, dou square f by dou y dou x. So when we move on to second order partial derivatives, you must remember there are 4 terms. One is first order partial derivatives is just dou f by dou x and dou f by dou y. When it comes to second order partial derivatives, there will be dou square f by dou x square, dou square f by dou x, dou x dou y, dou y dou x. Okay, then we will be having dou square f by dou y square, and then we'll be having dou square f by dou x dou y. So these many, when it comes to first order partial derivatives, there are 2. When it comes to second order partial derivatives, there are 4 second order partial derivatives. Now if you look at this a little bit more closely, you can see dou square f by dou x dou y is 6xy square plus 4x cube, and dou square f by dou y dou x is again 6xy square plus 4x cube. These two answers are same. So that is not a coincidence. Actually, it happens for continuous functions. So if your f is a continuous function, then these mixed partials, these are called mixed partials. Dou square f by dou x dou y and dou square f by dou y dou x are actually called mixed partials. So if your function is continuous, then these mixed partials will be equal. That is it is a stated result. Okay, it is a theorem, it can be proved, but we are not concerned with the proof as of now. So just remember, whenever your function is continuous, these mixed partials are going to be equal. Okay, now let's look at another question. We have a function like this: f of xy is equal to y square e raised to x plus y, and you are asked to find fxyy. So this notation may be a little bit confusing to you, but you must understand what is fxyy. You are first partially differentiating with respect to x, that you are differentiating with respect to y, and that again you are differentiating with respect to y. That is how you will arrive at fxyy. Okay, so let's start with the first step. Let's find fx. So what is fx? Fx will be, you must understand, y is a constant. Whenever we are partially differentiating with respect to x, y is a constant. So y square into dou by dou x of e raised to x is e raised to x, plus dou by dou x of y. What is that? It is 0. Dou by dou x of y is 0. So you just be having y square e raised to x. Now this I have to partially differentiate with respect to y. So what is fxy now? When I'm partially differentiating that with respect to y, so it is dou by dou y of y square is e raised to x. So it is 2y into e raised to x. Now again, what is fxy? Again, this term I'm partially differentiating with respect to y. So what is dou by dou y of 2y? It is just 2. So 2 into e raised to x. So the answer is 2 into e raised to x. If you miss this order, sometimes you might find things difficult. Okay, so fxyy means first you are partially differentiating with respect to x, then with respect to y, then with respect to y again. So in the other notation, what will this be? This will actually be dou square f by dou y square into dou x. So this will be the notation when we are writing it in the form of that dou notation. Okay, so this is just to make you understand of this notations. Now this is the theorem that I was talking about. Let f be a function of two variables. If f of xy and f of if fxy and fyx are continuous on some open disk, then fxy is equal to fyx on that disk. Okay, so for continuous functions, these two mixed partials will be equal. Okay, now we will do one more problem. We have to actually prove something here, in the sense that you are given a function u of xt. Okay, u of xt is equal to sine of x minus ct. So you are asked to show that this is a solution of the one-dimensional wave equation dou square u by dou t square is equal to c square into dou square u by dou x square. This equation is actually called the one-dimensional wave equation. This is the equation which governs the transverse vibrations of a string. Okay, that is, suppose if I am having a string which is fixed at two endpoints. Suppose if I am plucking the string along a given plane and then I am releasing it, the string starts vibrating. Okay, suppose I'm plucking it like this and I'm releasing it, the string will start vibrating. So this transverse vibrations of the string is governed by this one-dimensional wave equation. So you are asked to show that this given sine x minus ct is a solution of this equation. So what they are meaning to what they are asking you is to show that this u satisfies this equation. So what you have to do, you have to find dou square u by dou t square and dou square u by dou x square and show that both of them are equal. So let's find these partial derivatives. So dou u by dou t. What is dou u by dou t? It is dou u of xt is sin x minus ct. So dou u by dou t will be cos x minus ct into dou by dou t of x minus ct. What is that? Dou by dou t of x minus ct is minus c. Again, dou square u by dou t square. So again you have to partially differentiate this. So it becomes, so derivative of sine is cos, derivative of cos is minus sine. So minus sine x minus ct, and you already have a minus c, and then again when you are doing, you will have a minus c. Or I'll just, if it's confusing, I'll just write it this as minus c into cos x minus ct. So it will become a little bit easier. So you will be left with, okay, so you'll be left with minus c, and then here you again have a negative sign, minus sine x minus ct. Okay, I'll write that term again. So you have minus c into derivative of cos x minus ct is minus sine x minus ct into minus c. So you have minus c square sine x minus ct. Okay, now what is dou u by dou x? Dou u by dou x is cos x minus ct, and dou by dou x of x minus ct is 1. So it is as such. So what is dou square u by dou x square? That is equal to minus sine x minus ct into 1 again. So you can see the difference is just by this constant c square. So dou square u by dou t square is actually equal to my c square into dou square u by dou x square. Hence you have shown that the function u of xt equal to sine x minus ct satisfies the one-dimensional wave equation. Okay, we'll be stopping this video here. Thank you.